determine conditions on the real constant mu, that is this letter over here, so that 0, 0 is a center of this linear system. Okay, well, since we're doing this in preparation of classifying points that are not going to be in linear systems, where that's going to kind of be one of our ways to get around the fact that we might not be able to find an explicit or like a closed form solution, we have to know what it means to have this system at point 0, 0. So let's see, if I put, assuming this is x and this is y, so we could think of this as a horizontal vector, even though I like to keep them as vertical because I usually deal with vertical vectors, but the purpose is the same. If I say x prime is equal to minus mu multiplied by the x that they give me, which is 0, plus y, which is also 0, I get that my slope, my change of x with respect to the independent variable, which is in there, so this system is autonomous, is 0. And so that's x is a critical point for the first equation. Now, x and y is a critical point for the first equation. Now, if it satisfies also the second equation, then we can say it's a critical point for the system. So let's input 0 for x here, plus mu times 0 instead of y, and we get this. So we know that with this experimentation, we get that 0, 0 is a critical point right there. Okay, so now what are they asking us? Well, they want this to be a center. So how can this be a center? I'll show you the chart here. In order for this to be a center, we need to be on this axis, meaning the trace tau for 2 by 2s has to be 0, or in other words, the real part of the eigenvalues of the corresponding coefficient matrix of the system should be, I know it's a little bit of a mouthful, should be 0. So let's rewrite this in matrix form. So if we have an x prime and a y prime here, we can put this into the vector brackets right here, and that is equal to let's put some other matrix brackets a little bit bigger. This is going to be our coefficient matrix, and it's going to be my negative mu times 1 and negative 1 times mu. Okay? And then on this right side, we're going to have, and I want to show you where everything comes from. So I'll take the step by step. Here we're going to get an x and a y, because I really want you to understand, get a feeling for what we're doing. So were we to classify this, how would we classify the critical points? Well, what we would have to do is we would essentially look at this because I'm thinking if I should introduce a new method or not. I think not with this one. So we want to determine the conditions on the real constant mu so that 0, 0 is a center for the linear system. So in order for this to be a center, we want this to be satisfied. And we want the matrix here to not have a real part. So this is what we're going to try and do. Let's say that we want to solve the eigenvalue problem here. Why? Because if I call this X prime and I call this the A matrix, bear with me for a second, and I call this my X vector, I recognize that this is the system X prime equals A times X. And we can solve this, right? This, we can say, for example, let's try and guess that our X is K e to the lambda t. You don't have to do this every time. I'm just showing you where the eigenvalue problem comes from. Now, if I say that this is my guess, then what is it going to be X prime? Well, if I assume that this is a vector of constants, then X prime, which I'm going to write over here, is just going to be what I had before and the lambda, right? Lambda times what I had before. And that's going to be equal to A times, what's my X? It's going to be the K e to the lambda t. Well, now we realize that these will never be 0, so we can cross them out. And what we have left is I apply a matrix transformation to this vector, and it's the same thing as applying a scalar multiplication to the vector, which means that the vector is not getting knocked off of its span. So now we can say that A times K minus lambda K. Now, this is a matrix multiplication. This is not. So to make them the same dimensions, so to speak, I can put in an I matrix in here. And that has the effect of making the same dimensions. And that's equal to the 0 vector. Now, I can factor out this vector. And what I get is A minus lambda I right here. I close this, multiply it by the K vector, and the result is the 0 vector. So how can this happen? Well, either K is 0, and so whatever transformation I apply to it doesn't really matter. It's just going to be 0. Just like in scalar multiplication, hey, no matter what I multiply 0 by, 0 times 5, it's still 0. 0 times 10, it's still 0. Or the determinant of this is 0. The determinant of A minus lambda I is equal to 0. The determinant tells us how much that transformation stretches the area, a unit area. So an area subtended by I hat and J hat. And I encourage you to watch 3 Blue, 1 Brown's playlist on the essence of linear algebra, and in particular the determinant video, if you want to understand this concept a little bit better, because I feel like animations do a great job with that. And so now that we have this is the eigenvalue problem. I want to find the lambdas. And why are we doing all of this? Because we're realizing that we can write the system that we have in this way. And I need the eigenvalues to not have a real part. So I need to find a determinant that gets me eigenvalues with no real part by altering mu. And that's what they're asking us, because if we have no real parts, then the solution is going to revolve around a circle or an ellipse, but it's not, it's going to be periodic. So let's see what our matrix here is, and we get minus lambda 1 and minus 1 lambda. So mu 1 and minus 1 mu. This is what we had before, right? Well, now we want to solve for the eigenvalue. And I'm going to do it not with the trace, but just with the normal method that we've been using. So we subtract lambda from the diagonal, that comes from this equation. If you were to expand this, this would look like a, it would look like a with negative mu, 1, negative 1, and mu. And then we would subtract lambda, which we're trying to find, and then the identity matrix would be this. So if you distribute that lambda in, it would be here, and then if you were to make this subtraction, you get this matrix over here. So I hope so far everything is going good, and I know I'm making it a little longer than just finding the answer, but I really want you to understand where everything is coming from so that you have the tools to understand questions like this and answer them correctly, and then hopefully implement them for other things that you'll need this math for. So once you have this, to indicate that we're going to take the determinant of this, you want the vertical lines. So we'll put vertical lines, and that has to be equal to 0. So now, if I find the determinant, and I factor out the negative sign from this term over here, what I get is lambda plus mu times, well, I'm going to factor out another negative, lambda minus mu, right here. And then we have minus negative 1 times 1, and all of that is equal to 0. So let's see what that gets us. Well, these negatives cancel out, and then we have lambda plus mu times lambda minus mu equals, well, let's not skip steps. So minus negative 1, that's going to be plus 1, equals 0. So now if I bring negative 1, if I subtract negative 1 from both sides of this, what I get is lambda squared minus mu squared minus 1. And so how do I make this lambda have no real part? We just, let's add mu to both sides of this. I get mu squared minus 1. Now, if this is anything smaller than 1, then this whole thing is going to be negative. And when I solve for lambda by taking the square root, I'm going to have this stuff under it. So as long as this is less than 0, then we're going to have no real part. We're only going to have an imaginary part. So then I can add 1 to both sides of this inequality, and I can have mu squared is less than 1. And so mu has to be less than plus the plus or minus square root of 1, which just reiterates the fact that mu needs to be less than 1. Now, you have to kind of be careful with the inequality, because now if I say less than 1, less than plus or minus 1, if here we get something that is less than negative 1, we get like negative 2, that'd be 4 minus 1, and that would become real. So what we want to say actually is we mean to say that mu has to be between negative 1 and 1. And this should be our answer. I hope you understood where this came from. So now if I actually get a mu that is, let's say 1/2, what would happen? Well, let's write it down. So we're going to try and find the eigenvalues of that mu. And if we find the eigenvalues of that mu, what we're going to get is, sorry, of that matrix with mu 1/2. So we get negative 1/2 minus lambda, and then we get 1, negative 1, negative 1, and then we get 1/2 minus lambda here. 1/2 minus lambda. So what happens is that if I take the determinant, I can say minus out here, and I can say minus lambda plus 1/2, factor out a negative sign, open a new parenthesis, lambda minus 1/2, and minus negative 1 times 1 equals 0. What we get is this goes away, and we get lambda squared minus 1/4 plus 1. So we get lambda squared, and 1 can be rewritten as 4/4. So we get lambda squared is equal to positive 3/4. All of that has to be equal to 0. So when I add 3/4 to both sides and I take the square root, I get plus or minus the square root of negative 3/4, which is the same thing as plus or minus the square root of 3/2i. There is no real part. No real part. Which means that this matrix with this mu will be having a bunch of concentric trajectories based on our initial condition. And I hope this was useful. And I will see you, well, I'll do a part B so that I can show you this in CalcPlot and that you can better understand. I'll see you there.